Are you reading stuff and are you doing these things? The point of this exercise is to understand for sure that if I were to ever give you the joint probability distribution, you will never ask me anything more about a probabilistic scenario. That's the maximum you will ever want to know. That's all there is to know. Any question can then be answered if I were to give you joint probability distribution. Okay? Just as if I were to give you the models in which the knowledge base holds, the worlds in which the knowledge base holds, then I gave you everything that you ever needed to know in propositional logic. Okay? So anyway, that's important because to say that something has well-defined semantics, which for example Bayesnets will say here's a Bayesnet and it has well-defined semantics, I'll need to show you that there is a unique joint probability distribution that is defined by a given Bayes network. If I do that, then you know that it has semantics. That's what semantics means. Okay. So anyway, here's the, there are two variables here. These turned out to be Boolean variables, CA and TA. In fact, you can think of them as a cavity and toothache. It makes you happy. Okay. And then, so these are probabilities of cavity and toothache, cavity and not toothache, not cavity and toothache, and not cavity and not toothache. Those are the words. Okay? Right? So, what is the probability, the first probability? What's the probability that cavity and toothache is true? Because that I just gave you, that's 0.04. Okay? What is the probability of cavity? How did you figure that out? Yeah, basically this idea of computing PCA is by essentially summing over other variables in the joint distribution. This is called marginalization. Okay, CA, this is called a joint probability. This is because this is directly present in the joint probability distribution table. You just read it off. Anything else like CA, you get it by marginalizing everything else. So basically you're saying CA, probability of cavity, is probability of cavity and toothache plus probability of cavity and not toothache. Because the universe can be divided into those cases where toothache is present and those cases where toothache is not present. And so if you happen to know cavity and toothache and cavity and not toothache, then you know the total cavity probability. That's called marginalization. In fact, this is a very useful thing because given a big joint distribution and I ask a small query, normally what happens is you will have a joint distribution over 100 variables. Okay? And you're never going to ask queries over 100 variables together. You typically want to know, for example, a query such as, give me the probability that a particular variable will be true. To compute that, you realize that if I get you the joint probability distribution, you then need to sum out 99 variables. How many entries are you going to sum out over? 2 power 99. You see what I'm saying? Okay, 2 power 99 entries are going to be summed over to get the probability of that one variable. Okay, just because I say there is semantics doesn't mean that is the best way to compute something. In fact, directly computing anything from joint probability distribution is a dumb idea. Just as dumb as directly trying to prove things in propositional logic by drawing a truth table. That's the first principles way, but we'll find more efficient ways. Okay? So anyway, so PCA you can compute by essentially adding those two up. That's called marginalization. How about PTA? The same way. Marginalization. What about CA or TA? There basically you are saying probability of CA plus probability of TA minus probability of CA and TA. And where did you get CA and TA? Happened to be there here. Because if you have joint distribution, you know that number. So you could compute this. Okay, an interesting question actually is that why should one define R this way? Okay, that is, why should it be the case that probability of A or B is probability of A plus probability of B minus probability of A intersection B, A and B. And the textbook actually points out a very nice argument that is due to an Italian mathematician who essentially said, if you do not believe this, you don't have to believe me. You know, you can compute P, A, or B in a different way. Then I will be able to set up a betting game where I will be able to get all your money. You see what I'm saying? That's where it hurts. You know, it's like people get to say, we don't believe in evolution. We don't believe in this. It's not just a question of not believing or believing. It's like when it actually hits your pocketbook, then you start caring. Okay? And so, yeah, I don't like this kind of a formula. Fine, you don't need to care about it. Make up your own formula. Then I'll set up a betting game where you lose all your money. Then I'll see if you'll care or not. That's the best argument, actually, as to why A or B is defined that way. Okay. That's CA or TA. Now, what about CA and CA given not TA? So to do that, that's basically the first place where we are talking about conditional probabilities. Okay? And as I said last time, probability of A given B is defined as probability of A and B by probability of B. Right? Okay? So basically you're saying probability of CA and not TA divided by probability of not TA. CA and not TA, you know what it is. TA you already computed, again, from the joint distribution. Right? Okay? So you're able to compute this conditional probability. Anyway, by the way, the conditional probability is only defined if PB is not equal to 0. Because if PB is equal to 0, then that conditional probability will become infinite. That makes no sense for a probability to be anything other than between 0 and 1. Okay? Now, the interesting thing about conditional probabilities, since we are there, is notice that probability of A given B is this. Right? Now, what about probability of B given A? It will be probability of B and A by probability of A. So, two things. First, I can write probability of B and A. First of all, I hope you realize that and is symmetric. A and B is the same as B and A. Right? So, probability of B and A can be written as probability of B times probability of B, probability of B times probability of, probability of B and A can be written as probability of B given A times probability of A. Can also be written as probability of A given B times probability of B. Right? Because A and B is, this A and B is a probability of A and B times PB. This B and A is the same as A and B, which is probability of B given A times PA. So B given A times PA or A given B times PB. Okay, this just comes directly from that notation, that definition. Okay, and this, being able to write this actually has many advantages, it turns out. First of all, so I'm going to remove this. You got this, right? You agree, I didn't make up anything. So, the first thing I can do is that if I, and this is a very useful thing for us, if I have probability of A and B and C, okay, I can think of this as one quantity. And I can write this as probability of A given B and C times probability of B and C, which itself can be written as probability of A given B and C times probability of B given C times probability of C. Right? Okay? This I did not, this is just true. There's nothing, I mean, I just used the definition of conditional probabilities to do this. Okay, now the order doesn't matter. You could have written this. It's also equal to probability of B given AC times probability of A given C times probability of C. It's also equal to probability of C given AB times probability of B given A times probability of A. The order doesn't matter. All of these work. Do you see what I'm saying? And when I write this, I didn't make up any new theory of probability. I'm just using the definition of conditional probability. This actually is a very useful idea. This is, you should know this, but if you don't know it, now you know, because we're going to use it. When defining, the semantics of Bayesnet, we will realize that, remember, we all need joint probability distribution. And I can write the joint probability distribution as a multiplication of a whole bunch of conditional probabilities. And if you remember, and I'll say it again today anyway, but if you remember at the very end of last class, we saw Bayes networks have topology and conditional probability tables. So Bayes networks only give you conditional probabilities, it turns out. And so you somehow put those in to compute this. That's how we say there is semantics. Okay? This is basically called the chain rule of probabilities. So if I have probability of x1, etc. up to xn, I can write it as take any permutation of x1 to xn and stick to that permutation. Okay? So let's say I want to stick to the permutation x1 to xn itself. Then I can write it as probability of x1 given x2 up to xn times probability of x2 given x3 up to xn times probability of x3 given x4 up to xn, etc., etc., finally probability of xn. Okay? And you could do in a different permutation so that in the end you will end with probability of x7. That's fine too. All of them will be equivalent. Okay? None of this is new. This is stuff that's just elementary probability theory. I mean, I completely understand that you may have forgotten this because you haven't used it probably for a long, long time. Okay, but we need it. Okay? The second idea, so this is chain rule. Very useful thing. Okay? The second idea that I want you to understand, which is almost as silly except it has a person's name attached to it. Okay? And that is, if these two are equal, I just said, right, P and A is PB given A times PA. It's also PA given B times PB. If these two are equal, then I can say probability of B given A is probability of A given B times probability of B by probability of A. Huge algebra I did. And since I did this algebra, I should call it Rao's rule. Except the first guy who did it is Reverend Bayes. So it's called the Bayes rule. And you hear about Bayes rule everywhere. So why did Bayes become so darn popular just because he did this? I mean, it looks like elementary stuff. Anybody, even in his time, I'm sure people knew how to do cross multiplication. Right? Why is this so interesting? Why did he become famous and not us? You should always wonder that way. And the question is, so why this is interesting, it turns out, is think about it this way. Suppose you do it this way. P, disease, given symptom. So B is disease and A is symptom. Is probability of symptom given disease times probability of disease by probability of symptom. Suddenly I'm talking about medicine now. And actually doctors do just this, basically. Okay? So what are they doing? You have these, so to the extent we believe symptoms are caused by diseases rather than vice versa, if you somehow start putting water so that your nose runs, it doesn't cause flu. Okay, but if you have flu, it causes runny nose. So the causation theory is flu to runny nose, not runny nose to flu. Okay, so this is the diagnostic probability. Diagnostic probability. This is the causative probability. So this is, what is the probability that if I actually have flu, I will have runny nose. And this is the probability that if I have runny nose, what's the probability that I have flu? Okay? First of all, Bayes tells you that if you know one of these, you can compute the other one. If you know the diagnostic, you can compute the causative. And if you know the causative, you can compute the diagnostic. And the most useful way to use this is to go from causative to diagnostic probabilities, most typically. In fact, the word diagnosis, and when you go to a medical doctor, you expect them to do diagnosis. You know, my favorite example is, nobody ever seems to go to doctors and say, doctor, I'm suffering from flu, can you check if I have runny nose? Why don't you do it? Right? You know, if you can say, you know, I'm a great doctor, I will tell you whether or not you have symptoms if you tell me what diseases you have. You know, you would typically go out of, business very fast. Okay? The point, of course, is symptoms are actually most of the time observable. And furthermore, nobody really cares if they have a symptom or not. They want to know what disease they have and remove that disease. So doctors are basically trying to figure out, given your symptoms, what is your disease. And they depend on Bayes' rule. So now the interesting thing, of course, is actually, so you can think of all of medical textbooks and medical training is essentially giving them an idea of this probability, the causative probability. How likely is it that people suffering from flu will have runny nose? How likely is it that people suffering from cirrhosis of liver will have yellowness of nose? Things like this. That's what medical knowledge is all about. And then people will come with a bunch of symptoms and you're trying to figure out what their disease is. Okay? So you can think of causative probabilities is what makes up the medical textbooks, and your ability to throw them together to get the diagnostic probability is what allows you to charge exorbitant amounts of money to unsuspecting patients. Okay? Now, of course, one interesting question is, hey, why do we need doctors? You know, I have a symptom. Internet is full of pages which tells me what diseases cause this symptom. Okay, so I can self-diagnose myself. I mean, maybe you have too many homeworks due, so you're not spending time, but you come to my age, you have enough ailments, and you have internet available, so you check, you know, these are my symptoms, what are the diseases, and Google will tell you, you may be suffering from any one of these 18,000 diseases. And the more exotic, the more likely that I must be suffering from it. Right? Okay, so one of the interesting things actually that also makes us realize is, it's not the case that disease given symptom is completely equal to symptom given disease. It is symptom given disease times probability of disease by probability of symptom. And what happens when people actually go on internet and self-diagnose themselves, internet tells them quite well what this probability is. What internet doesn't tell you is what's the probability of having this disease in the area you are around. Okay? And so you just basically assume, oh, I'm pretty sure all diseases are equally likely. You know, I'm sure I could have either flu or Ebola virus. And, you know, both of them cause runny nose, so I assume that I have 50% chance of Ebola virus, 50% chance of flu. Okay? So this is essentially because you have no obvious place where you get prior information, priors. Okay? And by the way, this is also called the fallacy of prior. Fallacy of ignoring prior, I guess. And this basically is called a prior. Okay, so there's a lot of jargon we developed here. I could have shown it in different slides, but it's just one set of formulas here. I call this prior. Okay, so the prior, so basically before, so the patient just walked into your office. They didn't even start talking, you the doctor. They just walked into your office. You already have a probability as to whether they are suffering from flu or not. Then they say, hey, we have a runny nose. Then you're recomputing the probability that they have flu given that they have runny nose. So you, in some sense, you recomputed the distribution, the probability distribution for disease, given the evidence. Most interesting probabilistic queries are all about computing the distribution of a variable given evidence on other variables. Okay? And if I didn't give you any evidence at all, then it's prior. This is like without any evidence. If just people walk in, this is the probability that they have the disease. Then I know that they have. They have runny nose. So then I multiply this by probability that this disease will cause runny nose. And that would then be proportional to the actual probability that disease is present given this evidence. So this is called posterior. This is a word you will keep using a lot. And in fact, you can sound very informed in probabilistic communities if you just say posterior. Okay? So this is posterior, this is prior. And you are always computing posteriors given the evidence. Those are some of the most interesting queries. I mean, there's nothing wrong with these queries, but these queries are more likely to be the ones that you will be computing often. Okay? So this picture actually shows you that point. So for example, when the patient came in, okay, let's say the CA cavity has values. Maybe in this case, cavity is either true or false. Okay? So I guess this is true, this is false. This is false, this is true. Okay? And in the beginning, you're assuming, in this case, the prior is saying, this prior says it's equally probable. That means a random person walks in, they either have prior with the cavity with 50% probability and don't have cavity with 50% probability. This is only one of the priors. And this basically means you are living in an area where there is way too much sugar intake in the night. That's why about 50% of the people who just walk in have cavities. In normal areas, you actually expect that a random person doesn't have cavities. Okay? It's more likely not to have cavity than to have cavity. So in that case, the prior would have been low here, higher here. Okay? And then now they say, well, I have toothache. And then I recompute my probability distribution. This is the posterior of cavity given toothache. I mean, it's not exact, I'm just showing some curves saying there are probability distributions. Okay? And then they get some more evidence. Toothache as well as, you said toothache and then, you dentists have these funny things that they'll put to poke you on your teeth, right? And then when they try to poke, it gets stuck somewhere. And that basically means you actually have a cavity, right? It got stuck in the cavity. Okay? So if you have a toothache, plus you could have had a toothache because you just overate ice cream just before going to the dentist's office. You had no cat. There's no necessary. It's not necessary that toothache must always imply cavity. But if you have toothache and that thing gets caught in your tooth, then it's a much higher chance that you actually have cavity. So the dentist is likely to say, wow, you must really have cavity now. The probability that you have cavity is much higher now than probability that you don't have cavity. So then they will start doing the procedures such as root canals or whatever. Okay? So that's what we do. We normally, as evidence comes in, you are computing the posterior over certain variables. In this case, the variable of interest is cavity. Okay? And the way you do that is using Bayes rule. Because Bayes rule essentially tells you to multiply the disease, prior probability of disease, times the probability that the disease causes that symptom. Okay? Now, I'm going to remove all this. One interesting question is how thick should the medical textbooks be? You know, they have to remember probabilities, right? They have to remember these probabilities. They, of course, have to remember the priors too, and I'm sure they kind of say, oh, in Tempe area, cavity is like 30% prevalent. In Tempe area, Ebola virus is like, 10 power minus 13 prevalent, hopefully. Okay? So those are the probabilities. Those are the prior probabilities. Okay? Then, basically, the question is you need priors to be remembered, P of disease to be remembered. Okay? But you also have to remember P of, for each symptom, you need to remember symptom given disease. The probability that that symptom causes, and that disease causes that symptom. That's for if they open their mouth once and say we have this disease, we have this symptom. Now, suppose they actually say we have two symptoms. So in this case, essentially, let's say if there are M symptoms and N diseases, okay, there are N priors, one for each of the diseases, right? And then you also have M times N of these numbers. It looks, that's handleable. But now if people are allowed to give up to two symptoms, okay? And then if somebody says, I have both symptom 1 and symptom 2, that means I have runny nose as well as body aches. Okay, what is the probability that I have runny nose as well as body aches if I have flu? You may, if you just have these numbers, you will know what is the probability of having just body aches given flu, just runny nose given flu. You have this overwhelming temptation to multiply those two numbers to get the probability of runny nose and body ache given flu. But you can't. Normally you can't, because they can be correlated. So pretty much, if flu always causes both runny nose and body aches with the same amount of causation strength, then being told that they have body aches over and above runny nose doesn't increase or reduce your belief in flu. You see what I'm saying? So the real question then would be, if I have this kind of issue, probability of symptom 1 and symptom 2 given disease, I now need numbers. Apart from these, I need these numbers. How many of these numbers are there? M squared times N. But then, that's why actually doctors have very small windows where patients get to talk for 3 microseconds before they start diagnosing. Because you let them talk too long, they will start talking about, oh, this is also going wrong, this is also going wrong. And if they give you 2 symptoms, you now need to have M square N probabilities. They give 3 symptoms, you need M cube N probabilities. Okay? In the worst case, you need 2 power N probabilities. I mean, the exponential amount of probabilities. Okay? To avoid that, okay, so here, let's say, so this is probability of cavity given toothache and catch. You kind of could see that obviously, maybe this is actually increasing your belief in cavity. So in fact, the posterior shows the chance that you have cavity is even higher than before. Before being when you just had toothache. Okay, now I'm asking one more question. So basically, this patient is it doesn't stop talking. So now says, oh doc, by the way, did I tell you that Romney won? That is a symptom too. I mean, a lot of people actually think that's a symptom of a lot of things, but we won't get into that. Okay. Now the real question is, because he said Romney 1 or she said Romney 1, now is the doctor supposed to run and look into a bigger textbook, which gives probabilities of cavity given toothache, catch, and one of those really sad things happening, or one of those really good things happening, depending upon your belief. Okay? You need one more bigger table. Do you understand what I'm saying? Obviously, none of you think you should even care about Romney winning or losing. Not because you don't care about Romney, but because the current question is cavity. And you don't think cavity has anything to do with Romney winning or losing. So even though the world is all interconnected, hopefully some things are not very well connected. So Romney winning or losing typically is not connected to you having cavity. Okay? So really what you would like to do, most of you would like to say that, well, this is the same as this. You didn't say this is the same as this. You did, I at least convince you that if you have both toothache and that implement is getting stuck in your tooth, that means you have an actual catch. Then probably the chance that you have cavity has increased. Whereas if I tell you Romney 1, it didn't help one way or other. So it was actually the same as this. Okay, so to be able to do that, somebody must have told you that probability of CA given TA's catch and Romney is the same as probability of CA given TA and catch. That means somehow catch is independent of Romney winning or losing. If I already know the evidence about toothache and catch. That is the conditional independence assumption. In fact, here actually it's pretty much, probably it's reasonable to say that catch is completely independent of Romney, irrespective of what evidence has been provided, what additional evidence has been provided. That would be an absolute independence assumption. More general one is, if I already know this, giving this extra information doesn't help me in any way. It doesn't change my probability. Okay? So I need to be able to write down these kinds of conditional independence assertions, and that's what ultimately saves you from having to deal with a large number of probabilities. Okay, when dealing with large number of probabilities in the sense that, remember, for every number I'm showing you here, somebody went and got these numbers and put them there. So for this part of the course, we'll assume that some human basically wrote down, the knowledge engineer wrote down all the numbers. And they now give a whole number of numbers. In particular, if you are writing a medical expert system, which will use this kind of knowledge to do diagnosis automatically, you need to write down these numbers. And since you can't just make up these numbers, you have to ask people with medical degrees, what do you think is this number? What do you think is this number? And if you have like 10 diseases, 10 disease and symptom combinations, you are going to ask them 1,024 questions like this. At some point of time, they'll throw you out of your office. Especially when they realize that all these questions are eventually going to make them be out of a job forever, right? The secret, please tell me so that nobody ever needs to do medicine anymore. And all of you would be out of a job. Okay, and our little machines will be doing medical diagnosis. And they will certainly say, no, we're not going to tell you any of these numbers. But even otherwise, these numbers, there are just so many of these numbers, and it's very hard to come up with these numbers. Okay, so normally what you're going to actually ask people, so there are two issues here. One is there are too many numbers. And secondly, numbers of this type. What is the probability that cavity and toothache will be present? That means the joint probability distribution table entries. Those are extremely hard to assess for people. They have no clue, no intuition about what those numbers are. they may have better intuition about, if I know that this guy has flu, what is the probability that they will have runny nose? They might have a better intuition. Because in some sense, A, they would have seen it in experience. Okay? And B, even if they didn't see it in experience, just from the data, they can compute this more easily. You can set up experiments where you only get people who actually have flu and see which percentage of them happen to have runny nose. There is a way you got your probability. Whereas getting these kinds of numbers, you need to set up, if you have like 100 variables, you need to set up an experiment where each of these 100 variables is given a particular value. It's a very hard to control experiment. So typically we go with conditional probabilities to be assessed. Now just because you're assessing conditional probabilities doesn't mean that you'll only need to assess a few. You will still have to assess 2 power n in the worst case, unless there are conditional independence assumptions which hold in that domain. And what's obvious to you, that Romney winning has nothing to do with cavities, is not obvious to your program. And it would not be, if I tell you, would symptom S be, if I tell you that there is symptom S500 in addition to symptoms S1 to S499, and I want to know what is that, whether that will change a particular disease D300 probability. You won't know either because you're not doctors. Okay, so you need to assess these numbers, and there are fewer numbers to assess if you have conditional independence assertions. Okay. So, as I said, when I said last time, if you do have joint probability distribution, the example that you did is to convince you that if I ever give you joint probability distribution, you will then be able to answer any random query. Any query on those variables. Okay, and so then the question of course is, how do I get joint probability distribution while not using too many numbers? And notice that one of the things we discussed last time is, if in fact every one of the variables is independent. Okay, think about this. There are 10 variables. Okay, what is 10 Boolean variables? How many joint probabilities are there? 2 power 10. 10 to 24. All these variables are independent. How many joint probabilities are there?
10.
What?
10.
How many people think there are only 10 joint probabilities? Raise your hands, please. I did hear, but apparently it's because I questioned. You don't want to raise. The number of joint probabilities is still 1024. The number of joint probabilities is still 1024. If there are 10 Boolean variables, then there are 2 power 10 different words. And the probability of each of the words is given by the joint probability distribution. What is interesting is, if I just give you 10 small numbers, which is probability of x1, probability of x2, etc., probability of xn, these are numbers that are not directly present in the joint distribution table. You agree, right? In fact, I would say that these are conditional probabilities. These happen to be conditional probabilities where there is no given. Given nothing, the probability of x1. Given nothing, probability of x2. Given nothing, probability of x3. Given nothing, probability of x10. If I give you those 10 numbers, then you can telescope them into 1024 numbers, at which point you can answer everything. Conceptually, that's the idea. Do you get this? Okay? Joint distribution is always of the same size. But just because something is, so suppose I'm thinking, okay, here's this thing, okay, I'm thinking of 1,000 numbers. Tell me which 1,000 numbers I'm thinking of. I'm thinking of consecutive 1000 numbers starting from 101. Can you tell me now? Yeah. Are there fewer numbers? No. You just know exactly which 1000 numbers are because I told you, a very useful piece of information about the structure of those 1000 numbers. I'm starting from 101 and the consecutive numbers are being taken. That's what you're doing here. You are saying the joint distribution has a very specific format. Every entry in that joint distribution is a multiplication of these 10 numbers, or 1 minus each of those numbers. Right? If I basically the typical entry in the joint distribution would be x1 is true, x2 is false, x3 is true, blah blah blah. So you would multiply p of x1 times 1 minus p of x2 times p of x3 times 1 minus p of x4 if you care about x4 being false and so on. It's just a multiplication of these 10 numbers in different orders. I mean, some are positive, some are negative. I mean, some are direct variable probabilities, some are 1 minus the given number. You will get 1024 numbers. Now, you care about this because just getting these 10 numbers is way easier than getting 1024 numbers by asking people. Even if your program is going to use 1024 numbers, the input to the program is only 10 numbers. Okay, that's what we're trying to do. And in the worst case, the program uses 1024 numbers and it requires 1024 numbers as input. In the best case, it requires, such as it is best case, it requires only 10 numbers. In between, it might require less than 1024, but more than 10. And that would be because some things are independent of other things and some things are not. And you somehow figured out a way to write these conditional independence assertions compactly. Okay? So now finally, it should again, this slide was shown at the end of last class. I'm going to show it again and say, essentially, all you want is joint distribution, but joint distribution can be specified more compactly if you have conditional independences, if you know the independences that hold. Okay? And Bayes networks is a way to specify conditional independences as well as the numbers, such that from there you will get the joint distribution. Okay? And in particular, the topology of the Bayes network encodes conditional independence assertions. Specifically, the thing that you care about in a Bayes network is the following conditional independence assertion. If I have a node, if I have a variable x, remember that Bayes networks, at least the way they are shown, they are directed. There's directed arcs. This is a directed graph. Okay? In fact, directed acyclic graph. Okay? And so here I somehow put a link from burglary, directed arrow from burglary to alarm, earthquake to alarm, alarm to John calls, alarm to Mary calls. Okay? And the important local independence assertions that are implicit in that topology turn out to be, if let's say X only has parents Y and Z, immediate parents are Y and Z, and then Y has a whole number of other parents, W has another parent, J has another parent, okay, and similarly Z has some more parents, and so on. Okay, now if I say what is the probability of X given Z, Y, W, J, K, M, N. It is the same as probability of X given Z and Y. So I'm saying if you give me any of these or some of these, it doesn't make any difference. Because somehow, while these guys are influencing this guy, their influence is only through the immediate parents. This is only true for ancestors. In fact, what actually you are saying is X given non-descendants probability of X given, probability of a node given a bunch of non-descendant nodes that also includes its immediate parents is just the same as probability of that node given the immediate parents. That is the local assumption that is implicit when you wrote this network. Okay, now with just that assumption, and then the other thing that each of these networks has is for each node, I give conditional probability tables. And the conditional probability only has to tell me, since all that matters to me is my immediate parents, I only need to know when do I become true, given my parent status, what is the probability that I will be true? And what's the probability that I will be false? And of course, those two numbers add up to 1, right? Because you're a Boolean variable. And in this guy's case, John calls. If alarm is true, what is the probability that John calls? And if alarm is false, what's the probability that John calls? Now, from this, you also know if alarm is true, what's the probability John doesn't call? That's 0.1. And similarly, what's the probability that John doesn't call when the alarm is false? That's 0.95. But I only ask you these two numbers. When you show me this topology, I'll tell you, please give me these two numbers. And then for these two numbers, for these two guys, burglary has no parents. That means what's the probability that burglary is true given nothing at all? No evidence whatsoever. No ancestral evidence. That's basically also called the prior probability of burglary, P burglary. So I just give that one number there. And similarly, I'll give just one number for earthquake. Okay? And then here, on the other hand, alarm has two immediate parents, burglary and earthquake. So the conditional probability table must have 2 power 2 entries. So burglary true, earthquake true. What is the probability of alarm? Burglary true, earthquake false. What's the probability of alarm? Burglary false, earthquake false. Burglary false, earthquake true, burglary false, earthquake false. What are all those probabilities? The other interesting thing is the following. Because, one way of not getting people into trouble is never ask questions that will make them inconsistent. And equivalently, if I'm cross-examining you, I must ask questions that will show you to be inconsistent. Okay, lawyers will ask you the same questions in different ways until you kind of, roundabout way you admit that, what you said earlier is actually false. But if I don't want to know, I don't want to know anything about this entire network becoming inconsistent, then if I only ask these questions and you just put numbers in each of these tables, it turns out you would give a consistent joint distribution. It may not be what you wanted to give me, but it would be consistent. In that, essentially, there is a unique joint distribution that will correspond to any specific set of numbers that you provide me. And once I know the unique joint distribution, from that I can compute any probabilistic way. That's what you just did. Right? Okay? So by writing the Bayes network topology, I've already decided what numbers I need. And then I'll just then go and ask the doctors, tell me those numbers, if it's a medical expert system. Okay? Right? The other thing, of course, is in this particular case, notice that the dominating factor here is alarm because it requires 4 numbers. Because it has 2 parents. So the number of probabilities required to specify a network is of the order of the node which has the most number of parents. This is not human societies. There can be multiple parents for a domain, for a node. Okay? So in the worst case, what happens is when you have a worst case network, so this is Bayes network, right? So now it turns out that this is a general enough idea. Any random probability distribution can be written as a Bayes network. So if it turns out, what would be the case when I would need the least number of probabilities to specify this network? Least number of probabilities.
Nothing has any parents.
What?
Nothing has any parents.
Yeah, what does that mean? How does the graph look then?
Separate.
It's just a disjoint set of 5 vertices. It's a graph too. It's a graph with 5 disconnected. It's a 5 vertex graph with 5 disconnected components. So that would be the network that corresponds to the least number of probabilities. What would be the network that corresponds to the most number of probabilities? At least one node must have 4 parents. One node must have 4 parents. Now the temptation is to say everybody has 4 parents. If you do that, you will get cycles. And it won't be directed acyclic anymore. You see what I'm saying? If any node has 4 parents, if any node has n-1 parents, then that's the worst case scenario. You'll wind up requiring 2 power n probabilities. Okay? Right? Now, the tricky thing, of course, is I can't just make, the network have any random topology. The topology is supposed to be telling me about the domain knowledge. Just as these numbers can't just be made up. I mean, you have to ask the expert and get the number or somehow learn those numbers. And similarly, the topology also needs to be learned or be given by the experts. And when they're putting these edges, you should tell them, by the way, that this is what you're doing. If you think W has an effect on X over and beyond what it has through Y, then there should be another link from W to X. So normally, grandparents will get on your case by talking to your parents and saying, why is this kid getting so many bad grades? Hopefully, okay, to only your parents. And so then the parents will get on your case. So you normally only need to get your parents off your back. Sometimes there are active grandparents who not only will get onto your parents' case, they'll also call you and send you emails saying, what is going on? What is all these C's and D's in your grade point average? Then you now have to get off not only your parents off your back, but your grandparents also off your back. That's because they have a direct link to you. Okay? If they only influence you through your parents, this is fine. If they also are influencing you by calling you directly, then just having this means you're deluding yourself about the real domain. Okay? So the point I'm trying to make is the topology as well as the numbers are domain knowledge. Okay? And somebody who knows the domain gave it, or somebody learnt it from data. Right now we'll assume somebody gave it. When we get to the learning section, we'll talk about how to learn this if you just have numbers, if you just have data. Okay. So topology encodes the conditional independence assertions. And in this particular case, of course, if I have this, in this particular case, how many variables did I need? I had 1, 2, 4. So that is 4 plus 2, 6. And then another 2 plus 2, 10. Right? I'll quickly go to some other place. I'll come back to this. This is the last thing I'll do today. But okay. We'll again do this later too. But I want to give you, for the same domain, which has this as the network, this too is a network. Okay. The idea of making it, if you're asking the experts how to make the domain, the idea would be this. One idea is decide an order on the variables. Okay, so in this case, M, J, A, B, E, is the order I decided in this case. Okay, then introduce variables into the network in that order. For first comes Mary. And then whenever a node comes, you ask yourself, how many of the nodes that are already in the network is it directly dependent on in this domain, according to your understanding of the domain? And for any node that you are dependent on, you must put a link from that node to yourself. So the first Mary calls came. Obviously, nobody else is there, so there is no links into Mary. Then John calls comes. This is the burglary scenario. Remember burglary scenario? Okay. So my question is, if I told, you have John calls, if I just told you Mary called, would your probability that John called will increase or not? I mean, will change or not? So if I did not put a link now, then John calls will be just by itself. That means I only will provide prior probability of John calling. If I put a link from Mary to John, then I must give probability of John calling, given Mary not calling. 2 numbers instead of 1 number. I would do that if, to the extent I believe Mary calling changes my belief in John calling. Remember, nothing else has been told to you in the burglary domain. Okay, I just told you, you know the way the domain works, and you know that Mary called. Now, the John calling, would it depend on Mary calling or not? Of course, yes. Because if Mary called, you expect John calling more. If Mary didn't call, John may still call, but you expect it less. Right? So that's all. All I want is qualitative. I'm not talking about exact numbers. So qualitatively, John does depend on Mary calling, and so I put a link from Mary calls to John calls. Okay? Then I will introduce alarm. Now I need to ask myself, does alarm depend on Mary calling? Yeah. Put a link. Does alarm depend on John calling? Yeah. Put a link. Now I put burglary. Does burglary depend on alarm? Of course, because if I tell you that alarm is going off, you change. Again, this is, by the way, not causation. This is just correlation. In fact, I put it in the complete opposite order. I'm putting Mary calling first, then alarm, then burglary. Your causal theory of the domain is burglary causes alarm, alarm causes Mary and John calling. But if you don't know the domain, you don't know what causes what. And this is not at all surprising. Science is all about figuring out causative theories. And we had no idea how the world works, what causes what. All we knew is correlations. And so one guy found, for example, that the day he saw a black cat coming in front of him, he walked to his office and got hit on the head, and so he decided black cats cause problems in office. And so we made a theory. Nonsensical theory, but we made it from data. Right? We found a whole bunch of gays having HIV virus, and we just assumed gayness causes HIV-ness. This is in 80s. We are supposed to be much less stupider, but we still fell for that because coming up with causations are not obvious. What we first see is correlations. Okay. Anyway, so alarm causing burglary. So it's not causing burglary. If I know about alarm, would my belief in burglary change? Yeah. So I have to put a link. Okay. Now, if I know about alarm and I also told you Mary called, will my belief about burglary change? No. In which case, I don't need to put a link from Mary to this. So for example, in a different domain, where not only is alarm going off, but Mary has a separate phone call that she gets whenever there is something going on in your home. So she has additional piece of information about what's going on in the home. So if she calls, now you have a separate, independent evidence about what's going on in your home. Then you must put Mary calling connected to burglary. Notice how I'm deciding whether to put a link or not. It's about my understanding of the domain. And I already told you that given a completely new domain, nobody knows how it works. Okay? It's good for domains, this kind of an idea works if there is an expert for the domain, where people know how things work. And then you can use that knowledge. You're asking questions to them, and using that, you're putting those links. Okay. Then earthquake, and again, for that, I'll put a alarm to earthquake. Now, in the case of earthquake, if I told you alarm happened, your belief changes in earthquake. If I told you burglary happened, apart from alarm, would your belief in earthquake change? It does, right? Because burglary would explain alarm. So you don't need another explanation for alarm. Do you understand what I'm saying? So Breitbart, conservative columnist, died today. Okay? Then I tell you that, maybe if I tell you what is the probability that some left-leaning people who didn't like him did something bad to him? Reasonably high. Lots of people didn't like him. Then I tell you that Los Angeles coroner is saying he may have suffered from heart attack. Then what is the probability that some left-leaning guy went and did something to Andrew Breitbart? It could still have happened, this guy happened to have a heart attack at the same time as somebody is doing something bad to him. But you assume that's unlikely. We don't need one more explanation. We have one good explanation. So your belief for the other cause reduces. You see what I'm saying? So in this case, I have to model it. To be able to model it, I must put a link from burglary to earthquake. That's how I do it. Now, given this, you know the numbers you need. I need priors on Mary Calling and John Calling. I'm sorry, no, I need a prior on Mary Calling. I need John Calling given Mary, given not Mary. I need alarm given Mary John. I need burglary given just alarm. I need earthquake given burglary and alarm. How many numbers do you need? 1 plus 2, 3 plus 4, 7 plus 2, 9 plus 4, 13. 13 numbers for this. This was another network for the same domain. That only needed 10. So what did you learn from those two? What I learned from those two is, if you happen to know the causation in the domain, introduce the variables in the order of causation. If you happen to know the causation in the domain. That's a big if. In these kinds of domains, we know how things work, and so you know that burglaries cause alarms, alarms don't cause burglaries. Okay? And so, in that case, what I'm saying is, I picked any random order here, I would say pick the order that is consistent with the causality. Then you will wind up requiring the least number of probabilities. That's a good heuristic. This only works when you know the domain. And since you are modeling the domain, I hope you know the domain. Okay? So, if you introduce them in the order of the causation, you would wind up requiring only 10. If you introduce them in some random order, you require 13. If you introduce them in a different order, Mary calls, John calls, earthquake, burglary, alarm. And you have to reason this out to yourself. That in fact, when I introduced alarm at the end, I really do need a link from each one of them, because each of them is having additional influence by itself. You need to convince yourself of this. This is your domain understanding. This is not AI. This is how you think Los Angeles and humans work. And according to that, it will turn out that alarm will have 4 parents. This is the worst case scenario. Okay? So basically, a simple domain can be made more complex if you don't know how the domain works. Are you surprised? You shouldn't be, right? If you know how the domain works, you should be able to get by, knowing the independences that hold and causality that holds them. Okay, so what we did today essentially is we started from joint distributions, convinced ourselves that just joint distribution is enough to answer any queries. Okay, and then we also showed to ourselves that we also argued that Bayes networks essentially capture conditional independence assertions by actually saying what depends on what. Okay, and in particular, they have this particular local independence assertion. which says a node is independent of all its non-descendants given its immediate parents. And I'm going to take one slide, and that will be repeated again next class. And that's basically the semantics. The only reason I'm going to say it today is because I made a big deal about semantics, and I want to show you that slide. Okay? What I want to do is to say that if I have this network, I can compute the joint distribution uniquely. That's what I need to show you. Then you can sleep well. Actually, you'd be happier if I just let you go right now, but I think you'll be really sleeping well if you know how to do this. And so I need numbers of the type probability, burglary, earthquake, alarm, John calls, Mary calls. Probability, burglary, not earthquake, alarm, John calls, not Mary calls, and so on. Okay, so if I have this network, and if I'm trying to compute the single probability, probability John calls, Mary calls, alarm, not burglary, not earthquake. That's what I want to compute. And if I know how to compute this, I know how to compute any other number. Remember the chain rule, which I showed you earlier. So using chain rule, I can say this is nothing but John calls given Mary, alarm, not B, not E, times Mary calls given A, not B, E, times alarm given not B, E, times not B given E, times E. This, I just use the chain rule. I just use the chain rule. So I just need to know what these numbers are. Hopefully these numbers are present here. Okay, now I need this. Clearly I know this number, probability of earthquake, I can read it out from there. Okay, now probability of not burglary, again I can read it out from there because I know burglary, not burglary is 1 minus that. This I need, probability of John calling given Mary, alarm, not burglary, not earthquake. So John calling given all its non-descendants. These are ancestors, this is a sibling, non-descendants. Our big point is John calling given all its non-descendants is just John calling given its immediate parent. That's the point. So this is nothing but John calling given alarm. That is actually present. John calling given alarm is present there. Okay? Similarly, Mary calling given alarm, not burglary, not earthquake, is nothing but Mary calling given alarm for the same reason. That number 2 is present in this table. And finally, alarm given burglary and earthquake is present in this table. So I just multiply those 4 numbers, 1, 2, 3, 4, 5 numbers, and I got my probability. It's a uniquely defined joint probability. Go back and try to compute any arbitrary other combination and make sure you know that it can be computed. And the only thing you need to do is put the variables in the order of topological sort of this network. So the topological sort of this network will have burglary and earthquake in any order. They come before alarm, and then alarm comes before John calling, Mary calling. That's all I care. If you put them in that order, then use the chain rule, then use the local semantics of the Bayes network, you know how to compute the joint distribution entry. So in essence, this network corresponds to a unique joint distribution. And you know now that once you have a joint distribution, you can answer any queries. So much of what we'll do when we come back is how to do it more efficient. Okay? Thanks.